Good morning. Hi. You guys are troopers. 9 a.m. on Friday. Welcome to the last day of AltConf. As with the entire rest of the week, we've got a whole day of awesome talks lined up for you. Here we have Luis Solano, Philippe Cascarine, Robert Bonke, a design discussion panel. And then in the afternoon, we have Thomas Engel, Sal Mora, Josh Michaels, Victor Broido, and James Dempsey. Over at labs, we've got a reverse engineering lab and a jailbreaking lab, and then all afternoon we'll just be streaming from here and having co-working space over there. Okay, so our first speaker is a lead iOS engineer at Pixable. He loves open source community and TDD, and he created Noscilla, the easiest way to test networking code. Luis Solano.
Can you guys hear me? No? A mic? No? All right. Thanks for coming this lovely morning, 9 a.m. Hope you are not very sleepy. I am. I would like to start with a quote, and it's one of my favorite quotes, and it says like, clean code reads like well-written prose. And I like it. Who doesn't like clean code, right? And clean code matters because maintainability of the software, it's probably the biggest cost. And we spend a lot of time reading and modifying code. That's our most frequent activity. So by having clean code, we reduce this effort, we reduce this cost, right? But it's not only about economics. It's also about developer happiness. You get to retain more developers. Developers are less anxious about modifying their code if it's easy to read. And also super important, it allows you to iterate faster. You can modify features or add features faster and get those to the users faster. Let's say an example. Let's say that you have your code, pretty abstract, and then you have to add a new feature, add a concern, and it's just a few lines. So you decide to make room for it. No big deal. It's not necessarily the wrong thing to do. Then you just put them along with the rest of the code, and that's it. You ship it, done. And 2 weeks, 2 months later on, you find out that you need to actually modify this code or iterate with this code a lot, because business says that we have to do that. And then, well, you decide to extract it, and then boom, you've created an abstraction. Now you can reuse it, and you can test it separately, et cetera, et cetera. So a more concrete example, let's say that we have, for instance, a subscription class that you have to model when a user is paying for some service or not. Then you have to activate it with a code, only if it has not been activated yet, or you can suspend it so the user will stop paying for the service. Okay, these are your lines of code. You can check for the state, et cetera, a line along with the rest of your code. That is fine. But then when you decide to extract it, well, you decide to model it, for instance, as a state machine. So you create something like this, which is state machine. It has states, has events, et cetera. And then you use this to model that same state machine, but now it's decoupled from your subscription class. We know this. This is nothing new. We do this all the time. This is good. Now let's see how we can take this to the next level in terms of maintainability, in terms of making it easy to understand and read, because this is good, but it could be better. And let's see how we can write DSLs in Objective-C. Well, we have this new language this week, so I wanted to bring a little bit of that here. So let's do it in Swift otherwise. Yay. So yeah, I'm Luis Solano. I work at Pixable. You can find me on Twitter and GitHub. This is my handle. So please say hi. And for those of you who don't know, domain-specific language, a DSL, is language, as it states. But it's not a language, it's a programming language because we use it to tell a computer what to do. And it has the structure of a programming language. It is a specific, read, constrained to a certain domain or to solve a certain type of problems. It has a domain focus. It's focused on one specific domain, and it has limited expressiveness. It's not a general purpose language. You cannot do anything with this. You can just do a few things related to this domain. And that domain focus is what makes the DSL worthwhile. It's because it makes it small, and it makes it easy to implement and easy to use. If you were to implement a big language, the cost of implementing it and using it will go high, so that will be not as worthwhile. So yeah, we can take something like this, as we saw in our example, and we can add a thin layer on top of the abstraction that will make it easy to read, easy to, again, maintain, right? And this is really a thin layer. All the heavy work is being done by the underlying abstraction, what it's called the semantic model. And we can take something like this, these 8 lines of code that's not doing actually much, is wiring some objects together, into something like this. This is Swift. And see how fluid it is? It reads much better. It's just 1 line of code, although I have to wrap it here. So this is part of an open source project of mine. It's written in Objective-C. Model system machine. You can use it to model any arbitrary state machine. And a full example, it will read something like this, right? You have a state machine for your subscription. You model the transitions, given events, etc. And then you can even also define callbacks for when events happen, right? So this is all declarative code. It's good. I love it. So yeah, we take this, and the domain-specific language, again, is this thin layer that's sit on top of the underlying semantic model. And it's important to have this separation, have your classes, your code that implements your DSL, and your classes that implement the underlying model, because you want to maintain it separately, you want to test them separately, et cetera, et cetera. Another important thing about a DSL is those are declarative. And declarative programming is where we express what we want instead of the ordered sequence of steps to achieve the outcome that we want. And there is nothing wrong with imperative programming. Imperative programming is fine. It works. It's actually the only way that we have to communicate with a computer, like add this, compare that, jump there. Imperative is not the problem. The problem is my brain. The problem is our brain. You could say that our brains cannot handle the imperative programming scale. When the piece of software grows and you keep doing it in imperative way, then maintainability goes down. So we want to split things. We want to make APIs declarative to keep that maintainability cost low. So yes, DSLs are declarative. This is important. And some other examples of declarative programming are, for instance, even though they are not DSLs, are, for instance, auto layout. In auto layout, we express a set of constraints, and then we tell the system how we want our views to be put together, even if the view resizes, and then the system figures out how to make that happen. Another example is reactive Cocoa. We specify how our data flows in our app, and then the system figures out how to make that happen. Or SQL. We tell the system we want this data, and then the system goes and figures out how to retrieve it. So declarative programming for the win. Now, there are 2 types of DSLs. And those are the first and most important not most important. The 2 most important types is external DSLs. And external DSL is, given a system, for instance, an iOS application written in the main language, of course, Swift. An external DSL is something that lives outside of the main language, and you use tools like, parsers, etc., to create your custom syntax that may be a better fit for your domain-specific language, or you can use an existing syntax like XML, whether that's the right thing to do or not, or Ruby, or anything else, right? And you can parse it. Then what you could do is 2 things. You add a build step to your build, and what you do is you take these files, .myDSL, then you generate the code in the language of the main system. We'll generate Swift, that's one option. Or you could ship an interpreter with your app and then load these files at runtime. The second type are internal DSLs. And given our system in our language, Swift, an internal DSL, it's just a particular way of using this language. In our case, it's a particular way of using Swift or Objective-C, and it has to be valid, Objective-C or Swift. Those are the main types of DSLs. Now, why bother to create a DSL? Well, as I said, economics is a big reason. We want to make sure that our code is easy to understand, not only by us, but maybe our future new developers or future me. I want to understand my code as well. So lowering the maintainability cost is a big win. Developer happiness, but also fewer bugs. If we make a language that it's constrained to what you can say, then it's less likely that we're going to introduce bugs by saying the wrong things, right? That is also super important. But probably the most important one, the most important benefit is that you improve the communication. And I think this is huge. Because if you think about it, what we do, developers, is fill a communication gap. On one side, we have our users, we have our product managers, we have our customers, and these people speak in a high-level language. I want this feature to do this, I want this button in this color, etc. And then on the other side, we have the computer, or an iPhone, or an iPad. They speak low-level language, like I can sum up things, etc. And then our job is to fill a communication gap. Now, we cannot tell these guys, hey, please learn this low-level language, because effectively we'll be telling these guys to learn how to code, and they will be doing our job, and then we don't get to get paid. But on the other side, we can teach the computer or these devices to learn to understand a higher-level language and raise the level of abstraction that these computers can understand. So, the gap, it's effectively smaller. And now, it's not that our job disappears, but our job now is much easier. So that is a big win. Now, when to go ahead and implement a DSL? Basically, when you could expect one of these benefits that I outlined. But some heuristics is, if you're going to modify a lot, some piece of code, maybe consider adding a DSL to it. Or maybe if the communication's hard with your product manager or some other stakeholder, you want to probably make it, close that gap and make it easier for you to translate between these two parts. Or maybe if it's a critical part of your system, you think, oh man, this cannot break. So you put your time, you get it right once, and then all you have to do is use the DSL in different ways to modify that part of the system. And now, for the rest of the talk, we're going to go and take a look at some techniques to actually write DSLs in Swift. So weird to say Swift and not Objective-C. Okay, so the first technique is Swift methods. And this is, they're similar to Objective-C in what you can interleave the arguments and the method name. So you can create a sentence of a given length with some particles for the sentence. And instead of, naming these arguments as parameters, you can use them to form like kind of a sentence, right? And I definitely rather have this than this, right? This will be the underlying semantic model that I mentioned. And by the way, it could be written in Objective-C, and you can write your DSL in Swift. Why not? The DSL will be forming all this stuff under the hood. But you don't need to instantiate classes or do all that verbose stuff. All you need to do is something like this, and then you're done. Now, these Swift methods or their Objective-C counterparts are good for DSLs because they are simple. They're just out of the box, the most simple thing you can think of. But they're limited to sentences of a fixed size, right? You can only say, in this case, a sentence with 3 particles. An alternative is what I think is the workhorse of internal DSLs, is method chaining. This is Nothia, another open source project of mine, where you can use it to stop network requests. And what this does is you're telling the system to, hey, when a test is making a request to this specific URL, I want you to respond this specific way. So you can unit test your networking code. And in Objective-C, this was even possible. Like you would just put add symbols before the strings. But it's a total hack. Now with Swift, this is super easy. It's straight out of the box, because this is how Swift methods and functions look. In this case, the entry point is just a plain Swift function. Note that in functions, you don't have the labels for parameters, and you can force the caller to put them if you want, putting a hash before the label of the argument. But in this case, it doesn't make a lot of sense. It reads pretty well. So that's good. And then all you have to do is return an object that has the AndReturn method, and that method will return self. And then you can keep chaining method calls to that object, to that same object, right? Then you can rely on the type system. If you want to, at a certain point, only force the user of the DSL to just use some other type of particles for your sentence, and you can return another object of another type that only has those methods. So you can rely on the type system to only allow the user of the DSL to say valid things. That is a big win. In this case, for instance, at a certain point, the AndReturn particle, it returns something that it's referring to the response. Although before, it's referring to the request. So if the request has this, has that, then return, and then we're talking about the response, return this with this headers, with this body. You can see probably here better, right? The first part specifies how the request should look like, and then after the return, it's all about the response. Cool, moving on. Another good thing, we have this in Objective-C as well. It's extensions and name categories in Objective-C. And it's pretty cool. You can add any method to any class, even though it's defined by the system. We can still do this. Sorry. And in Swift, it's better because we can add these methods to literal types, like integers or strings or floats. We don't have to box them. So it's much cleaner. But, adding a method to an object, for instance, it can be dangerous, so handle with care. But in this case, we see how we can add for instance, the should method to any object. So now we can make expectations in our test about any object, right? For instance, you can do it something like this. Instead of category, it's called extension, and the syntax is much cleaner. And this will add the should method to any object. Cool. Moving on. Literals. Doesn't have to be super complicated. You can just literals, lists, dictionaries as part of your DSL. For instance, here we're using a dictionary to pass a set of headers to match against a request. Simple as that. Now, if you think that literals are cool, you can use them in Swift with your own types. And this is kind of an obscure feature of Swift. For instance, let's say that you have this DSL for a thermostat. Nothing wrong here. You're passing a temperature and maybe a human-readable time, whatever. But what if I tell you that these methods don't take a double or a string? This takes temperature and a date, because we want the type system to help us. Okay, but then how are you passing a double or a date or a string? Sorry. Well, there are some special protocols in Swift that define how literals convert to certain types. And because we have extensions, we can add these protocols to your own types or any other type, like a state. Let's see how that works. For instance, for the case of the float literal, we have this protocol defined by Swift, right? And it says that every time I see a float literal, and it's tried to be stored as a different type, I'm going to check with that type if it conforms to this protocol. And if it does, I'm going to call this method to get the value of the right type. We implement it like this. For instance, we're adding it to our temp class. And we have to define that the literal type is going to be represented by doubles in our case. And then what we're going to get to this convert from float literal is a double. And then we're going to return a temp. And all we have to do is go ahead and return that object. And now we can use, if we want to assign a double to a variable of type temp, we can just go ahead and do that. The system will do it will convert it for us. Or if we want to pass it as an argument to a function, it will work as well. And there's these protocols. We can use it to, use it with integers, with floats, strings, with logical values, with string interpolation, arrays, and dictionaries. So there's quite a variety. Sadly, it doesn't support to add your own literals. It will require a lot of hackery. But it's definitely a powerful tool that you can use. Also, again, handle with care. It could be confusing. All right, let's talk about blocks or closures or whatever you name. You can use them to add hooks to your DSL, imperative hooks. In this case, we're adding a callback. And, this case gives us the perfect context to add different bits of imperative code here and there. If we were to express that block in a declarative way, it will make the DSL like a general purpose language. So it is okay. And now with Swift, we can use the trailing closure syntax where instead of passing the closure as part of the argument list, we can put it outside and with curly braces out of the method call. And if it's the last argument, that block, then you get this nice syntax. And it reads like control flow. Really nice addition. You can also rely on the time inference system to, you don't have to add a lot of noise to your DSL, so that is definitely good. And it's still type safe. Cool. You can use them as well for giving context. Another open source project too. You can use it to generate test objects for test. And first you have to define a factory to, how you construct these objects. And you use this block to give the context that, okay, in this context we're only talking about how you construct the user. Mention two features like KVC or subscripting. Especially good because subscripting, you can have multiple subscripts for different types. Good thing. Syntactic sugar. It doesn't add much. The semantics of your program are not going to change if you add particles like with or and. But they add this nice readability or fluidity to your DSL. Just consider them. Now, a cool thing of Swift, it's operator overload. There's a lot of them that come right out of the box. And then you can use them. You can define functions that, given these two types, when they're put together with this specific operator, then this is what the program is going to do. So you can override the plus symbol for your vector objects. Or, if you put it together with method chaining or extensions, then you can have a type-safe way of defining speeds. And if you don't think that those operators I show you are enough, Swift allows you to define your custom operators. You can use them. You can define operators with any of these symbols, any size, I believe. And then you use something like this. And now we have this operator, this weird rocket. And then you can do anything with it. You can overload it for any type. And this, it's okay to add these operators, but again, this can be confusing. Just think about, those operators are part of the domain, are part of the jargon that the domain specialist, if you will, would use normally. Go ahead, no doubt. Otherwise, again, handle with care. Because, if you have this operator and you have a problem, good luck with that, right? So a piece of advice, and this. I've heard this by Martin Odersky, the creator of Scala. Always provide textual versions of your operators. That's provide a Googleable way of Google name for your operators as well, right? So you have two implementations. Yeah, SEO. That's right. Okay, so one other case where we can rely on the type system is, I had this library and I got a feature request saying, hey, I want to use regular expressions to match requests as well. So if instead of a string I pass a regular expression to the URL, the request will match if the URL of that request matches that regular expression. So it only supports string right now. So like, okay, what do? I know. I just changed it to ID. I would just change it to any object. Right? And now I can pass anything. I can pass strings. I can pass regular expressions. And I would just downcast them inside my implementation because it's mine. And, everything will be good. The problem, though, is that you can also pass empty arrays, you can pass objects, you can pass anything. Now, it's harder for the user to use the DSL because the type system doesn't convey specifically what types you can use with it. So my proposed solution is to add a protocol to an existing class. All you have to do is define a protocol that, in this case, have the matcher method. And you can add extensions to the types that you want to support. In this case, string. It will return a string matcher. To any regular expression, it will return a regex matcher. And then all I have to do is change the signature of my function to accept one of these matchable types. And now I can pass strings. I can pass regular expressions. But I cannot pass any of these. So that's good. Again, rely on the type system to make your DSL less error-prone. All right, so I think this is all I got. Small recap. DSL is just a thin layer on top of an abstraction. Make sure that you have that abstraction first, and then you separate that abstraction from your DSL. It has limited expressiveness. Don't aim to create a DSL that does a lot, or is even a general purpose language. That would be a rabbit hole. It will make your code more maintainable, reducing the cost, increasing the developer happiness, and improving the communication, as well as letting the users of the DSL introduce fewer bugs. So that's all I got. Thank you. Any questions? I'm going to grab my coffee over here if you don't mind. Come on, it's Swift. It's new.
I have a smart question. I like this idea of extending base system objects with the protocol there, what you did with the matches. Are there any other things that you could do in similar ways that could also allow expressiveness in DSLs? I mean, I was looking at something like Spectre and Expector and trying to see what we could do to improve that. Like, how can we minimize even more syntax but still get similar levels of expression?
Well, I kind of exhausted the different techniques I got for Swift here. I don't know. I cannot think of anything right. I mean, but if you implement that in Swift, operator overload is definitely something I would consider, because it adds this succinct syntax to DSLs. That's probably one of the newest things and more usable.
I guess I have one more question if no one else has one. Do you think there's anything specific to Swift that we can use to make more DSLs as opposed to like taking on an Objective-C library and like trying to port it over? Like if you had to rewrite Nothilia, like is there anything you would do different now?
Well, absolutely. To begin with, I wanted as part of Nothilia this method chaining with the dot syntax. And I have it in Objective-C, but it's a total hack. So the entry point is a C function that returns an object. And this object, here, let me bring it's a total hack. So stop request in Nothilia, it's a C function. And that returns an object. And that object has the with headers method and the and return method. But those methods don't take arguments. They return a block that take a dictionary, in this case, that returns self. So, I mean, when you use it, you don't realize it's implemented that way. You say, okay, this is weird syntax. But I take the cost of maintaining it, and I don't mind. Now in Swift, you just do methods and take arguments, and as you would do, and it's perfect, right? The reason I wanted to do that in Objective-C is that with Nothilia, you can make sentences of an arbitrary size. And I don't want you to have like 16 open square brackets if you are going to, make a big sentence. Because, after all, DSLs are easy to read, etc. So I don't want you to have that, right? So I would take the burden of, crazy maintainability thing. But yeah, that's definitely something different. Also, I mean, again, operator overload, it's a thing that we don't have in Objective-C. That's cool. We don't have the precompiler macro. I'm kind of sad, although it's a total hack again. But it allows you to do also crazy things that are come pretty handy with for DSLs. So yeah. All right. Thank you.
All right, we'll just take a quick break, and then we'll be back with our next speaker, Philippe Cascarine, Robert Bonke, a design discussion panel. And then in the afternoon, we have Thomas Engel, Saul Mora, Josh Michaels, Victor Broido, and James Dempsey. Oh, over at Labs, we've got a reverse engineering lab and a jailbreaking lab. And then all afternoon, we'll just be streaming from here and having co-working space over there. Okay, so our first speaker is a lead iOS engineer at Pixable. He loves open source community and TDD, and he created Nosilla, the easiest way to test networking code. Luis Solano.
You guys hear me? No? A mic? No? All right. Thanks for coming this lovely morning, 9 a.m. Hope you are not very sleepy. Important, it allows you to iterate faster. You can modify features or add features faster and get those to the users faster. Let's say an example. Let's say that you have your code, pretty abstract, and then you have to add a new feature, add a concern, and it's just a few lines. So you decide to make room for it. No big deal. It's not necessarily the wrong thing to do. Then you just put them along with the rest of the code, and that's it. You ship it. Done. And 2 weeks, 2 months later on, you find out that you need to actually modify this code or iterate with this code a lot, because business says that we have to do that. And then, well, you decide to extract it, and then boom, you've created an abstraction. Now you can reuse it, and you can test it separately, et cetera, et cetera. So a more concrete example, let's say that we have, for instance, a subscription class that you have to, the models when a user is paying for some service or not. Then you have to activate it with a code, only if it has not been activated yet, or you can suspend it so the user will stop paying for the service. Okay, these are your lines of code. You can check for the state, etc. A line along with the rest of your code. That is fine. But then when you decide to extract it, well, you decide to model it, for instance, as a state machine. So you create something like this, which is state machine. It has state, has events, etc. And then you use this to model that same state machine, but now it's decoupled from your subscription class. We know this. This is nothing new. We do this all the time. This is good. Now let's see how we can take this to the next level in terms of maintainability. I am. So yeah, I would like to start with a quote, and it's one of my favorite quotes, and it says like, "Clean code reads like well-written prose," and I like it. Who doesn't like clean code, right? And clean code matters because maintainability of the software, it's probably the biggest cost. And we spend a lot of time reading and modifying code. That's our most frequent activity. So by having clean code, we reduce this effort, we reduce this cost, right? But it's not only about economics. It's also about developer happiness. You get to retain more developers. Developers are less anxious about modifying their code if it's easy to read. And also super important.
Good morning. Hi. You guys are troopers. 9 a.m. on Friday. Welcome to the last day of AltConf. As with the entire rest of the week, we've got a whole day of awesome talks lined up for you. Here we have Luis Solano.